Alrighty, so moving on to some of our trig identities. Most of these trig identities you are familiar with and we've already talked about from our unit circle back in Unit 10, right? These reciprocal identities we have already introduced. Cotangent is the reciprocal of tangent. Secant is the reciprocal of cosine. Cosecant is the reciprocal of sine. And then we've also already introduced how tangent is y over x. If tangent is y over x, then tangent's the same as sine over cosine, and cotangent is x over y, which means cotangent is the same as the ratio of cosine over sine. Okay. These last two sets of identities we're going to introduce today. And what we're going to do is we're going to start with our unit circle up top here, where we have any point on our circle, xy. And we first found these ratios by constructing our right triangle and using x squared plus y squared equals r squared, using our Pythagorean theorem, right? We also talked about how sine of theta is y, cosine of theta is x, and tangent of theta is y over x. Okay, so what we're going to do is we're going to substitute in sine and cosine where we see x and y, and see if we can write a different equation using sine and cosine, and possibly introduce some new trig identities. So when we substitute in, remember cosine is x, so cosine of theta squared plus sine of theta squared equals, remember our r on our unit circle for our radius, the unit circle always has a radius of 1, so we can just substitute 1 in. And let's simplify this down, and this is actually going to be one of our first trig identities. Cosine squared of theta plus sine squared theta equals 1. This is one of our Pythagorean identities, Pythagorean trig identities. You can see it's this first one right here. Okay, and I'm going to show you how we can get the next two by just manipulating this equation. And we're going to do that up above. Okay, so our trig identities we're currently finding up top right now. What we can do is we can just take this equation let's paste it right here and paste it right here. Okay, so if we have these two same equations, it's a little bit bigger. What we can do is we can just divide this whole equation by sine squared theta, and we're going to have a pretty similar equation here. When we divide by sine squared theta, we get cosine squared theta over sine squared theta plus sine squared theta over sine squared theta is just 1 equals 1 over sine squared theta. Okay. And there's a couple ratios in here that we can simplify. We know that cosine over sine is, it's one of our trig identities down here. Cosine over sine is cotangent. We're going to rewrite this as the cotangent squared of theta plus 1 equals, and we know that the reciprocal of sine is cosecant. So we can write this as the cosecant squared theta. This is another one of our Pythagorean identities, which you can see down there at the bottom. Cotangent squared theta plus 1 equals cosecant squared theta. And then our last Pythagorean identity is going to come from taking this same equation and dividing the whole thing by cosine squared theta. Now we're left with 1 plus sine squared theta over cosine squared theta equals 1 over cosine squared theta. Let's simplify some of these down by using our properties again. Remember, sine over cosine is tangent, so we get 1 plus tangent squared theta equals, and the reciprocal of cosine. The reciprocal of cosine is secant, so this equals secant squared theta. So 3 new properties that come from this Pythagorean theorem on our unit circle, or anywhere graphing these points on our coordinate plane. Okay, 1, 2, and 3, and you can see all 3 of those down here under your Pythagorean identities. The last one I want to introduce on here are these negative angle identities, and instead of using algebra to prove or highlight these negative angle identities, I just want you guys to take a look at Desmos here. So if I open up Desmos and we were to graph y equals the sine of x, it looks like this wave graph that we have right here, right? We spent plenty of time graphing the last 2 sections. Perfect. Okay. Well, if we were to put a negative in front, that's going to reflect it over the, remember, a negative a value reflects over the x-axis and makes it open down. It would look like that green graph now, right? So we now just reflected it over the x-axis. Well, the same would be true as if you reflect over the x-axis, reflecting over the y-axis. Because these are periodic, it's going to look the same exact. It's going to look like the same exact graph if you're reflecting over the x. So if I highlight my purple, it's the same exact graph that we had up here. And the way you can tell is these overlap. So reflection over the x-axis looks the same as a reflection over the y-axis when you graph both of these functions. And that's all this theorem is stating here. So that if you have a negative angle input, that's the same as multiplying the whole ratio by a -1. Okay. All right. Let's go ahead and solve a couple of these down here. So what you're asked to do is prove each of these trig identities. And what that means is you are asked to solve one side of the equation until it equals the other, using all of these identities up here above. Another way you can, or a helpful hint for proving these identities, is you might want to simplify the more complex side first. Okay. So if you're looking at number 1, the more complex side of the equation is clearly the right side. Right? There's more going on here. On the left side, we just have the secant of theta. So let's start manipulating these ratios and see if we can get some stuff to simplify. Remember, we can rewrite cosecant as 1 over the sine of theta. And we can rewrite tangent of theta as sine of theta over cosine of theta. Hopefully you can see now that we have 2 terms that we can cross multiply here and eliminate. And we're just left with the secant of theta equals 1 over the cosine of theta. And then using your reciprocal identity, 1 over the cosine of theta is the same as the secant of theta. And you have proved that trig identity. Secant of theta equals cosecant of theta times tangent of theta. Okay, let's try one more, and then I'll let you guys try 3 and 4 on your own. Let's try 2 together. Again, the more complex side is the right side of this equation. Tangent of theta equals, let's rewrite secant as 1 over cosine. And let's rewrite cosecant as 1 over sine. And we're left with a tangent of theta equals, when you have a complex fraction, multiply by the reciprocal. So 1 over the cosine of theta times sine of theta over 1. And we have tangent of theta equals sine of theta over cosine of theta, which is the same as the tangent of theta. Okay. So you want to make the equations equal, proving the complex side of the equation, or simplifying the complex side of the equation first. Okay, why don't you guys try these next two on your own. A hint, the left side is more complex here, and the right side is more complex here. I'll pause, or I'll let you pause the video, and then work out 3 and 4 on your own, and I'll put the solutions up with all of the work right after. Go ahead. Okay, for number 3, all you could have really done here was sine of theta times cosine of theta over the sine of theta. And you are going to get your two sides to eliminate, and you're left with the cosine of theta equals the cosine of theta. For number 4, a little more work here. Something you could have done is you can move parts of these Pythagorean identities around. Something you might want to move around is if you see the secant squared theta, you can bring that 1 over, and you're left with sine squared theta times, for secant squared theta, we can go ahead and just multiply by the reciprocal. So that would be 1 over cosine squared theta. Okay, and then if you're using these Pythagorean identities up here, you can see that secant squared theta minus 1. If you were to move the 1 over to each side, you can see that the tangent squared theta equals secant squared theta minus 1. So we're going to replace that with tangent squared theta. When we multiply here, we get sine squared theta over cosine squared theta. And again, you're left with tangent squared theta equals tangent squared theta, and you prove that identity. So what you might notice is you might need to change one or both sides of the equation to get them to equal each other. Okay, let's continue some more of these simplifying examples. Let's do a couple of these together. Again, using those same identities up above. For number 1, sine squared theta. Again, you can take any of these Pythagorean identities and rewrite them. So if we have sine squared theta, and we want to get sine squared theta in terms of cosine, you could subtract cosine squared theta to both sides. And you're left with sine squared theta equals 1 minus the cosine squared theta. And the whole reason we want to rewrite that as 1 minus cosine squared theta is because we have 1 minus cosine of theta in the denominator. And we know that this binomial, we can't just eliminate here. We know that 1 minus cosine squared theta came from 1 minus cosine theta times 1 plus cosine theta. You can treat that just like a difference of two squares if you had something like this. 1 minus x squared factors to 1 minus x times 1 plus x. Now you can eliminate a binomial because they're the like terms. You can eliminate 1 minus cosine theta, and we're just left with 1 plus cosine theta. Okay. Not letting me minimize my screen. There we go. Okay, let's try another. Let's try 2. Secant of theta minus tangent theta times sine of theta. Let's get these all in terms of sine or cosine. So secant we can rewrite as 1 over cosine of theta. Tangent we can rewrite as sine theta over cosine theta times sine of theta. This is just over 1. Okay, let's multiply those fractions. We have 1 over cosine of theta minus sine squared theta over cosine of theta. Great, when you're subtracting fractions like 1 over 2 minus 5 over 2, remember you can just rewrite those with the same denominator. Combine like terms in the numerator, which we don't, so we just write 1 minus the sine squared theta over cosine theta. If you manipulate that Pythagorean identity, 1 minus sine squared theta, we just move sine squared theta to the other side. We have cosine squared theta equals 1 minus sine squared theta. So we can rewrite the top part of this equation as cosine squared theta over cosine of theta. And now when you have one monomial, this is one term, this is like having x squared over x, we can eliminate that squared and we're just left with cosine of theta. Okay, there are 4 more examples on here. Why don't you guys work these out on your own, pause the video, and then I will put all of the work on here so you guys can see each of the solutions. And we'll talk about one last thing, and then we are done. Okay, pause the video, work these 4 out, go ahead. For number 3, really the only thing we could have simplified was what was in parentheses. And we can rewrite tangent and cotangent as these 2 ratios. We want to write them with a like denominator, so that would be cosine theta times sine theta. And then we need to multiply each side, so sine squared theta and cosine squared theta. And then we have times sine theta cosine theta all over 1. Hopefully you can see here that we can rewrite this sign. I'm sorry, there needs to be a plus sign in here. We can rewrite that sine squared theta plus cosine squared theta as 1. So we have 1 over cosine theta times sine theta times sine of theta cosine of theta over 1. And you're just eliminating like terms that are across from each other, and you actually could have reduced this whole expression all the way down to 1. Okay, for number 4, 1 plus secant squared could have simplified to tangent squared theta, and 1 minus sine squared could have simplified to cosine squared theta. Tangent can be rewritten as sine squared theta over cosine squared theta. Cosine squared theta can be times cosine squared theta over 1. We have like terms across from each other, so we're left with sine squared theta. And then our last 2 here, you can break these up, put parentheses around these first 2 terms. We get 1 plus tangent squared theta. If you go look up at these Pythagorean identities, 1 plus tangent squared theta just equals secant squared theta. So we get secant squared theta. For 6, cosecant is 1 over sine, and tangent is sine over cosine, so we were just left with 1 over cosine, which simplifies to secant the reciprocal. Okay, one last thing I want to make note of on here. If you get directions, and you're going to get some directions that say express in terms of cosine theta, or express in terms of sine theta. If that's the case, you just want to take your answer that you simplified all the way down and rewrite secant of theta or secant squared theta in terms of cosine. So then that would make your answer for number 5, 1 over cosine squared theta. For number 6, secant of theta, if you wanted to express it in terms of cosine, that would be 1 over cosine of theta. For number, say, 4, if you wanted to rewrite in terms of cosine, sine squared theta, you could rewrite as, well, go look up here. You could rewrite sine squared theta as 1 minus cosine squared theta. If you just move this to the other side. So we would write this as 1 minus cosine squared theta. If it says express in terms of cosine or express in terms of sine, you want to make sure your answer has sine or cosine in it. Okay. That's it for this section. There's plenty of examples on the homework. I gave you all the odds, so please check your work, and I can answer any questions you have during office hours.